Welcome back to today's tutorial. In our exploration of the decimation in time, which is the DIT fast Fourier transform algorithm, we have discussed its basic concepts and the divide and conquer strategy it employs already. So if you have not watched my previous video, please do well and go and watch it before you come to this video. So now we are ready to dive deeper into the algorithm's implementation, starting with the fundamental concept of the butterfly, which is the butterfly diagram, right? So these are some key points that we have to take note of the butterfly diagram. As I said, the butterfly diagram is a geographical or graphical representation of data flow, right? Data flow, and calculations are performed in the FFT algorithm, right? FFT algorithm. One thing that you have to take note is that. So the second one is that it helps us to visualize how the input sequence are being divided. The division of the input sequence. The division of the input sequence, right? Yeah. Input sequence. Input sequence. And also processed and combined at each stage of the fast Fourier transform computation. As you may like, let's say you know about butterfly, right? The name butterfly comes from the shape of the diagram, right? The shape of the diagram. I'll draw the diagram here so you'll see it. The shape of the diagram, which resembles a butterfly with wings. A butterfly with wings. You know, I can't draw a perfect butterfly, so well, but the shape will show you since you have seen some before. Yes. In this algorithm, the butterfly diagram will illustrate data flow for the decimation in time strategy that we are going to use over here, right? And then each butterfly in the diagram represents a stage in the fast Fourier transform computation. That's one thing I have to know. Each butterfly represents a stage, right? Each butterfly represents a stage. So in this stage, two complex numbers, what is the representation as the rings of the butterfly, are combined using trade-off factors to produce two new complex numbers. So aside that, the only thing that you can do is that you illustrate it on the butterfly diagram. You trace the data flow by showing the arrows, and then you label it using the trade-off factors. From there, things will become easier and simple for you to go with. So let's proceed without wasting much time to start with a 2-point DFT example. So consider the fact that we have 2-point DFT, which we can have the input to be x of n is equal to, let's say, x1 and then x2. When we are labeling this, we have this one x of 0 and then x of what? 1. As I was explaining in my previous tutorial, right, the even part is this, and then the odd part is what is this. So if we have to draw a butterfly diagram, you have to draw the input aspect here. X of 0, even comes first and then odd comes second. So when you want to draw a butterfly here, the simplest way that we can draw will be at this point. And now my butterfly goes here, and then my butterfly comes here. So as you can see, this is a butterfly with two wings, the upper wing and then the lower wing. Right, then the output comes here, x of 0, x of 1, and this x of 0 and then x of 1 represent our x of k. Right. One thing that you need to note is that the trade-off factors are labeled at the lines that forms the rings of the butterfly. But one interesting thing that you have to notice that always the down line is having a negative of 1. The down line is having a negative of 1, right? And because it's a decimation in time, always the up line has a magnitude of 1, and then the line, the diagonal line that connects the top line is also having a magnitude of 1. So mostly, or most at times, we don't label them, we leave them. The most important ones that we need to label, is the one that I'm going to show you. So as I said, we don't need to label the top ones. That's why I'm deleting them. So the most important one that we need to always label is the denominator, or the down line here, and then the up line here, in the case of the decimation in time. Please take note of that. And as I said, we have not labeled this one yet, but always the down line has a magnitude of -1. So let's look at something here. If I have a normal n equal to 2, and I'm doing the computation, I'll compute two trade-off factor, omega n0 and omega n1. But because this algorithm reduce the number of complex multiplication, complex addition, or reduce into 2, we are going to use the trade-off factor divided by 2. We are not going to use the entire trade-off factor, and therefore the trade-off factor that we are going to use for n equal to 2 is no longer omega n of 1 and then omega n of 0, as we do for the direct computation and others. But this one is going to be using n over 2, of which this is where the efficiency comes in, right? And then I explained in my previous tutorial that the trade-off factor in this one is omega n of 2 and then m of k, right? I've already talked about that. And therefore, if we rearrange the trade-off factor omega n0 and omega n1, the one that this algorithm is going to use out of it for number of decimation is omega n of 0. That's the first one. And therefore, I'll do my indication here, and then I'll have my omega 2 of 0. I brought 2 here because n is equal to 2. And this n equal to 2, that's the reason why I placed it over here, is that it goes across this line. When it reaches this junction, parts go here and parts go here. So this part has a label going to the top and has a label going to the down. And remember that this has already -1 magnitude. So when it goes here, it goes as omega 2 0. When it goes here and multiply by the magnitude, it has negative omega 2 0. So let's go ahead and then proceed with doing that. Let me redraw the diagram here. X of 0, x of 1. And then I have it here, I have it here. I'll get this one here, and I'll get this one here. And as I said, -1 here, and then we have omega 2 of 0, of which this is going up here and also going down here, right? So now this is what we have, and then output is x of 0, x of 1. Since I have this one over here, we are going to get our output s of k, which are these ones. So if you want to do the inverse DIT FFT, which is inverse decimation in time, by using this same butterfly diagram, the only thing that you need to change is the trade-off factor. You have to find a complex conjugate. So in that case, omega 2 of 0 is going to be omega 2 the conjugate of 0. But if it happens that the trade-off factor is a real number, then it means I don't have a conjugate. If a real number, then you need to change the sign. And then remember that in the normal computation, it was over n, 1 over n, summation and co. Therefore, if n is equal to 2, the final state is going to be 1 over 2, and then 1 over 2 for the inverse aspects. The first one is the normal for it, but this one is for the inverse. And in that case, the output, the sequence s of k that they are going to give it to you will be here. It will be decimated over here and put it inside. So that is how the decimation in time for 2 points FF of t DIT algorithm look like. So in that case, we can say that, okay, let's try and simplify it. For the normal one, if I want computation x of 0, this x of 0, it will be equal to, this one is running here with a magnitude of 1, which is of x of 0. And this one, it's also going up here with a trade-off factor coming up here, which is omega 2 of 0, and then the number itself is what, x of 1. And then when I want this x of 1, which is the output, 1 is equal to, what number is coming here? The top one, x of 0. And then it's coming down to this point. You get me? And then the next one I need is plus. What is the trade-off factor is here, so it's also coming here. The trade-off factor 2, 0. And remember, it's a negative magnitude 1 is already here, and it's coming with 1 here. So it's multiplied by negative x of what? 1. So at the end of the day, we are going to get x of 0 minus omega 2, 0, x of 1. This illustrates whatever derivation we did in my previous video, right? This illustrates whatever illustration we did in my previous video of which reflect the symmetrical nature of the trade-off factors. So if I compute this, I don't have to waste my time write this formula again. I can just write this one minus this one straight away and get it. If it is in case it is the inverse IDFT FFT by using this algorithm, as I said, this S of k will be our input, and therefore the same procedure, we get x of 0 plus omega naught, and then here it's a conjugate, omega 2, here is a conjugate, and then x of 1, and then the same time x of 0 minus this one, this is a conjugate of 0, x of 1. But remember that this one is being 1 over 2 because the number of points is 2, and here is 1 over 2. So these are the equations that you use over there. And because per our previous tutorial, omega 2 of 0 is equal to 1, we are going to get x of 0 plus x of 1 for the first part, and then x of 0 minus x of 1 for the other part, for the Fourier DFT. For the inverse DFT, we are going to get 1 over 2, right? X of 0 plus x of 1, and then x of 0 minus x of 1. So I hope you get it up to this point. So thank you for watching, and see you in my next tutorial.